All right, everybody. Very good to see everyone here. Welcome back to semester 2. How is everybody doing? Everybody ready to be back? Seeing thumbs up, doing good. Okay, very good. Very good. How was everybody's break? Did everybody have a good break? Good break? Okay. Okay. Well, very good. So, welcome back to semester 2. And welcome to, this is a new module. We're actually in further physics now. So this is lecture 1 of further physics. Now, in some sense, this is very much a kind of direct continuation of what we were doing last semester with intro physics. But I should ask, do we have anybody who is parachuting in to further physics who hasn't done intro physics? Was everyone done intro physics? Okay, great. So that's great. If you've all done intro physics, then hopefully this should all be pretty familiar, okay, in terms of how it's going to work. Of course, we're going to be learning lots of new, exciting physics. So I should mention, if you've been kind of eagle-eyed, we do have a different code for point solutions, just because we do have a different code for the module. So as I'm sure you can read, today we're going to be focusing on charge and circuits, and really for a big part of this semester we're going to be thinking about electronics, electrical circuits, electricity and magnetism, that sort of thing. Now, for those of you following along on the textbook, so we're kind of kicking things off this semester with unit 13, so introduction to electricity. So I think, like I said at the beginning, this year it's roughly, we did kind of the first half of the book last semester. We're working on the second half of the book this semester. So if you want to get a bit of a steer for what to expect in the next few weeks, you can have a look at the next few units, see what we've got there. Okay, so what we're going to be building up towards over the next few weeks is understanding electricity and electrical circuits. That's where we're going to be going. And we're starting today by thinking about charge and circuits. Now, has anybody done charge and circuits, this kind of stuff before? Okay. Just a few people. Great. So sort of drawing circuit diagrams, that kind of stuff. Has anybody done that before? Okay. Now, there's a few different places people do this. Where have people done electronics, circuits, that kind of stuff before? What kind of courses have people done that before in? Sort of A-level physics? Okay. Has anyone done any of this in other courses other than A-level physics? Sometimes there's kind of other courses where people do it. Oh, yeah? The college access course. Oh, okay, access course. Okay. So that might be also sort of covering some of this sort of stuff. So yeah, we're going to be building towards electronics and circuits. Okay, so it's good some of you maybe done some of this before, but then also if most of you seeing this for the first time, also absolutely fine. Okay. Now, I like to start with, a picture with some kind of connection to what we're going to be thinking about. So today, the picture that I got over here, I got this picture of the Aurora Borealis, this really beautiful picture taken from the International Space Station. Here you can see all these really beautiful colors here. Has anybody seen the Aurora Borealis before? Has anybody seen this? Okay, so quite a few years ago, I was very, very lucky. I had the chance to actually go and see the Aurora Borealis in real life. And the colors, they really are just like this across the whole sky. It really is huge, extraordinarily beautiful. And we actually went in a year where there's what's called a solar max, so a year of maximum solar activity. So you get the most intensity. So of course you can see the Aurora Borealis from the ground. And if you're in the International Space Station, you get a really extraordinarily amazing view of the Aurora Borealis. And this is all caused by charged particles from the sun interacting with the magnetic field of the Earth. So today we're going to be learning about charges, charged particles. Later in the semester, we're going to be learning about magnetic fields. So I thought this was a nice picture that really kind of sums up a few of the concepts we're going to be learning about over the next few weeks. And actually, as a bonus link here, so of course this picture was actually taken from orbit, And towards the very end of the semester, we're going to be learning about the physics of orbits there. One last thing I'd like to just point out on this is something I really like about this picture. You can really see clearly here. Can you guys all see that there? That's the Earth's atmosphere, just how extraordinarily thin the atmosphere of the Earth is. You can really see that very clearly from this picture from orbit. So I thought this was a nice picture to start with, illustrating some of the concepts that we're going to be thinking about today and in the next few weeks. So that's a bit of a kind of big picture idea. Let's focus a bit on specifically what we're thinking about for today. Now, by way of illustration for this, I've got this really beautiful picture of the planet Jupiter. I guess the actual planet itself, you've probably seen something like that before, but can you guys all see the cool stuff going on near the pole there? So we get aurora on the planet Jupiter as well. So Jupiter has one of the most spectacular, certainly one of the largest, one of the most impressive magnetic fields in the solar system, and you get very, very impressive aurora on Jupiter as well. So I think it's really cool that we see that on Jupiter as well as on planet Earth there. So this is a bit of a plan for what we're going to be thinking about today and what we're going to be thinking about later in the week. Okay, so we're going to start by thinking about electrical charge. Exactly what is electrical charge in physics? Of course, what are the units? What are some of the physical properties related to it? Okay, and we're also going to be thinking about current. Okay, so the physics that happens when we start getting charges moving. This is when it gets really interesting. Now, later in the week, we're going to start thinking about voltage, power, and resistance. Okay, so that's mainly what we're going to be thinking about next time. But I guess some of you guys, you've seen some of these things before in the coursework, right? So maybe you've seen some of this before, seen some of the equations before. We're going to be learning a bit more about the physics of it this week. And we're also going to be thinking about what we call circuit rules. So when we're making electrical circuits, what are the rules for where the current is going to flow? Now, I think I'd really like to emphasize today is the physical connections, okay? So where's everybody who's done a bit of electricity, a bit of circuits before? Okay, so I think what can quite often happen if you're doing circuits for the first time is that there's a small handful of equations, a few relationships, quite a lot of seemingly arbitrary rules, and you can kind of memorize them and solve some questions, okay? So what I'd really like to emphasize over the next few weeks when we're thinking about electrical circuits is not to approach it as a set of rules and numbers and tricks to figure out what's going on in the circuits, but to really approach it from a physics sense, okay? So really building these physics connections, because this is still a physics module. It's a physics course. We're learning about physics, not directly electronics. So all last semester, you know, we're thinking about energy and forces and motion and all that good kind of stuff. So I'd really like to approach these concepts in exactly that same sense. So we're still thinking about forces, still not trying to just memorize things, okay? But the difference is now we're seeing how they apply to charged objects. So last semester, we didn't think about charged objects before. We only thought about objects that have mass. So the difference this semester, we're really just putting charge into the mix. And we are going to see that what we do get coming out of this is some quite neat little rules. And if you like, you can memorize them, use them to solve questions with electrical circuits. But what I'd really like to emphasize is that we're going to be making these physical connections so that everything we're learning about when we're learning about circuits, they're part of a kind of bigger picture of physics. Okay, that's the kind of plan for today, this week, and a large part of the semester. So I think that's all I want to say in terms of a kind of overview where we're going. So I think let's get things kicked off, starting a little bit about electricity. Does anybody know when the kind of story of electricity begins, when we kind of really start thinking about things being charged? Any thoughts? Anybody got any ideas? Might be kind of surprising. So we often think about electricity, you know, it's quite a modern phenomena, but the story of electricity, I think it really kind of starts with the ancient Greeks here, okay? They were the first to really coin this phrase of electricity. And where we get this word from is actually the Greek word for amber, which in Greek is called electra. And what the Greeks noticed is that you get these very kind of beautiful stones, but sometimes things stick to them. So sometimes you get like little bits of feathers, and they stick to these particular kind of rocks that they called electra. So they seemed to be attracted to them. There was this force of attraction between these two things. And the stones called electra, we now call amber. And that's actually where we get the phrase electra, electricity from this Greek word for amber. So I always like to know where these words come from. I think it's kind of interesting in its own sense. But it also helps to start to think about physically where our understanding of charge, where our understanding of electricity begins. And it really begins here with just this observation that some things, if you rub them together, then they kind of stick together. Has anybody done the demo? You get a balloon and you rub it on stuff and it sticks to your jumper and it sticks to your hair. Anybody done that one? Okay. And has anybody done the one, when you rub your socks across some carpet like this, and then you get a door and you get the little zap? Has anybody done that? You know what I'm talking about, right? And you get the electric shock. And then has anybody done also, you can build up the charge in a similar kind of way, and you can zap someone else. Has anybody tried that? Okay, yeah. So if you haven't, this is a kind of fun thing you can try already. So it works best on some kind of quite cheap carpet, and then your socks, and you kind of rub your feet along there with your socks. And then when you get to someone, you can kind of zap them with a little bit of static electricity. So that's kind of something fun to try. So that's what we get when we get charge building up on things, okay? So you can do that, with amber or, with socks. I also saw, it can happen with a cat over here. I think this expression, I think we can all relate to this expression sometimes, right? If we get charge building up, and I guess the cat it's jumped in this box of polystyrene here, and now it's all stuck. So there's this attraction. We now know that in order to get things attracted like this, we need a charge imbalance to build up. Okay, so if two things don't have any charge, then there's not going to be any attraction. But if we build up some charge by moving electrons around, moving electrons from one place to another, we can get a charge building up, we can get things wanting to stick to each other. So that's static electricity. It's quite fun. You can kind of zap people with little static electric shocks. You can stick bits of polystyrene to your cat. But clearly for practical purposes, there are certain sort of physical limitations. It's quite fun for sort of demos and that kind of stuff, but you can't, make a kind of modern industry based on static electricity. In order to do that, we need to get the charge flowing, okay? Now, if we think about this kind of situation here, when we have some polystyrene sticking to a cat or something like this, let's think about what this means for something to be charged, okay, to have built up a charge. So suppose we've got a solid object, and let's suppose we have a positive charge built up on this object, okay. What can we say about the electrons and the protons in the object, okay? Now, I'll get the question going. Have a think about this one with the people around you. We'll see what everybody gets for this one. If you're not sure about this one, think about where we're going to find the protons and the electrons in an atom, and which one we're going to be changing if we're maybe rubbing two things together, building up a charge difference between two objects. Okay, let's see what everybody thinks for this one. What's going on with our positively charged object here? Okay, so looks like most people going for option B over there. So we had several possibilities going on here, okay? Now, the convention is that, and I guess the name gives it away a bit here, that in an atom we've got protons, okay, and they're positively charged. But they're in the nucleus of the atom, so in the middle of the atom. And in general, in an atom, however many protons we have the same number of electrons, okay? And the convention is we say an electron is negatively charged and the charge on the electron, it's negative the charge on the proton. So if we have the same number of electrons and the same number of protons, there's not going to be any charge overall, okay? But if we start adding one or the other or taking one or the other away, then we're going to build up a positive or negative charge. So if we see what's going on here, so our hypothetical object, it's positively charged. So one way we could do this is by gaining protons. If we're kind of throwing protons, extra protons into our object, potentially that could build up a positive charge. So I can see why people might be thinking about this one. But the issue is that in general with an object, we're normally not messing around with the nucleus of something. Normally in kind of day-to-day life, the nucleus just kind of sits there and it's the electrons on the outside that are moving around, okay? So if it's positively charged, that means it's probably lost electrons, okay? So very well done to everybody who gave that question a go, especially if you spotted it, that it lost electrons, okay? So just remember, okay, protons have a positive charge, electrons, the convention is we say they have a negative charge, okay? So very well done, everybody, with that one. So that's the basic idea that was going on with, the block of amber when it's attracting things, or, with the cat. Maybe there's an imbalance in the electrons, so there's that charge difference, and then we get that attraction there. Now, of course, the ancient Greeks, they didn't know what was going on there. It was just these kind of nice rocks that feathers would stick to, okay? But now, of course, we know that if an object is positively charged, it must have lost some electrons. Now, let's start thinking a bit about the units for charge, okay? So, of course, we've got particular SI units for charge, okay? We've got some options here. Maybe you've seen some of these before. I'll get this question going. Let's see what everybody thinks for the SI units for charge. So if you're not sure with this one, just a hint that one of these is the SI unit for current. Okay, so that might help you to eliminate one of the options. All right, let's take a look at the responses. Let's see which of these is the SI unit for charge. Let's take a look here. Okay, so nobody's going for B and D. Some people thinking about A, some people going for option C. Now, I can see why people might kind of be drawn to option A there, the ampere. Does anybody know what option A is the units of? Does anybody know what's that the unit of? Current, very good, okay. So the amp, it's the unit for current. So you may well have kind of heard it when people are talking about charge. It's actually the SI unit for current, okay. And we're going to see what current is in just a moment, okay? Now, does anybody know what the Dalton is a unit of? Anybody seen this one? Oh, okay, interesting. And what about the Becquerel? Has anybody seen this one? Has anybody? Radiation, yeah, very good. Unit for dose of radiation, very good, okay? So I guess by the process of elimination, we're left with the Coulomb, C for Coulomb as the unit of charge there. So that's the SI unit for charge, okay? So very well done, everybody, with that question. That's what we've got for our unit of charge. Now, as we're going to see, 1 Coulomb of charge, it's actually a big old chunk of charge, actually. If you're messing around with a Coulomb of charge, that's quite a lot of charge, could be really quite dangerous, okay? So we're going to get a bit of a sense of how much charge is 1 Coulomb of charge in kind of just a moment, okay? But very well done, everyone, with that one. That's our SI unit for charge, okay? Now, as a few people spotted, this one over here, the ampere, this is the SI unit for current. And it's very related to charge, but current, it's the rate of flow of charge. So maybe if we've just got some current and it's just sitting there, might be a Coulomb of charge, might be a millicoulomb, but if it's just sitting there, there's no current. In order to get some current, we've got to get this charge moving. So if we've got some wire, we've got the charge moving through the wire, that's going to give us some current, and we can measure that with amps, okay? Now, this is kind of quite interesting. So current, it's defined as the rate of flow of charge, okay? So which of these equations describes this relationship mathematically? Now, the convention is that we use, a Q for charge and we use an I for current. I mean, I guess obviously we can't use C for both of them. That would be kind of even more confusing. So, we use a Q for charge and an I for current. That's just what the convention is. So if we've defined current, it's the rate of flow of charge. Which one of these equations here describes that relationship mathematically? Okay, let's see what everybody thinks for this one. So if you're not sure about this one, it might help to try the reverse question and think, how is current related to charge? And then do the algebra and reverse it. Okay, that might help you to see which of these is the relationship between charge and current. Okay. All right, let's see what's the relationship between charge and current over here. See what everybody thinks. Okay, so nobody's going for C and D. People mainly kind of split between A and B. Now I can see why these might be a bit kind of confusing here. So that's why it might be useful to think about this the other way round. Okay, so if we look at this definition, so current is the rate of flow of charge. Okay, so if we kind of took this problem the other way around, we said, okay, current I, so rate of flow, that means is equal to our charge divided by time. Okay, so I is equal to Q over T. So when you rearrange that equation, what you get is option B here. So Q is equal to IT. Okay, so very well done everybody who gave that question a go, because I think everybody is thinking along the right lines there. Okay, but it's just that so Q is equal to IT. Now, if you've seen an equation a bit like this before, quite often instead of relating charge and current this way, they're related, with I is equal to Q over T. But it's just an equivalent way of writing down the same thing. So what that means is, if we've got maybe 1 amp of current over here, so maybe our I is 1 amp, and we wait for 1 second of time, that means we're going to have 1 coulomb of charge passing through our wire, okay? Or equivalently, if we've got, 1 amp of current and we wait for a minute, that's going to be 60 coulombs of charge flowing through our wire. That's what this equation means, okay? So very well done, everybody, with this one. It might help if, we try a numerical example, put some numbers in here, okay? So suppose we think about like a USB charge. I guess everybody's got a USB charger, right? What you use to charge your phone. Now, suppose on our USB charger, the maximum current might be, 500 milliamps. Okay, 500 milliamps of current. Now, the charge on an electron, absolutely tiny here. So 1.6 times 10 to the minus 19 coulombs. So the individual charge on an electron, really unbelievably tiny, okay? But if we know that that's what the charge on the electron is, and we know how much current's flowing through our wire, the 500 milliamps, we can work out how many electrons are flowing through our wire each second, okay? So remember, this is the relationship between current and charge. So it's the same equations on the last slide, just rearranged, okay? You might have seen that before. So current, rate of flow of charge, so Q divided by T there, okay? So I'll get this question going. Let's see what everybody thinks. How many electrons are flowing through our wire every second in our USB charger? So the math with this one might seem a bit tricky because, the charge on the electron, it's really small, can make the whole thing seem a bit tricky. Just take it step by step. It might help to solve that equation for Q, work out what Q is, then work out how many of those electrons we're going to need to give us that much Q. All right, let's see what everybody gets for this. How many electrons flowing through our USB charger every second? Let's see what everybody thinks. Okay, so nobody likes option B, but then people thinking could be A, could be C, could be D, okay? Now, this question can be a bit tricky because there's a few different pieces of the puzzle to unpack here. So let's start with the current over here. So 500 milliamps, okay? So milli, thousandth, okay? So 500 milliamps means this is half an amp of current. Okay, so we could have written this as, 0.5 amps of current. Now remember, 1 amp means 1 coulomb per second, okay? So if it's half an amp, that just means half a coulomb per second. So every second, our USB charger is giving us half a coulomb of charge, okay? Now half a coulomb, actually quite a lot of charge every second there. So we want to get half a coulomb of charge, but each electron, it's only giving us, 1.6 times 10 to the minus 19 of a coulomb. So a tiny, tiny amount. So to work out the number, this n that we need, we just need to divide that half a coulomb by the charge on the electron there. So half divided by 1.6 times 10 to the minus 19. And when you do that, what do we get? We get this option C, okay? So very well done, everybody who gave that question a go, because it can be a bit tricky, okay? And it's very easy to kind of get things a bit confused, okay? Just a bit of a quick pro tip whenever we're thinking about kind of extreme values like this, okay? So this charge, absolutely tiny, 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 tiny charge on the electron, okay? Where's the hole? Oh, it's back, okay. Oh, is this a touch screen? I just won't touch it anyway. Okay, where was it? Yeah, so the point is, this is a tiny, tiny charge, okay? So if we want to get half a coulomb of charge, we're going to need a lot of them, okay? We're going to need, in technical terms, we're going to need a whole bunch of them, okay? So 10 to the minus 17, this is less than 1 electron, okay? This is, 10 to the minus 17th of an electron. So it's very easy to get things confused, get things a bit the wrong way around. But remember, we need a lot of electrons, okay? So it's got to be, kind of ballpark closer to this, okay? And when you do the math, that's what we get. We get option C there. So very well done, everybody, with this question, okay? So that's the basic idea of, when we've got electrons flowing. Now, has anybody done any, making circuits yourself? Maybe you've made like a light bulb. Anybody done that kind of stuff? You get the battery and the wires, the whole bit. Anybody done any of that before? Okay, a few people. I always quite enjoy that kind of stuff. So whenever we're making circuits, very often we hear about making circuits in series. Okay, has anybody heard of that before? Talking about a circuit in series? Okay, so we'll see what this means, okay? So suppose we're making something in series. What this means is that all the components, they're connected sequentially along the wire. So maybe we've got like a light bulb and some other bits and pieces, and they're all connected in a line, okay? So suppose we have some components connected in series. What can we say about the current going through each of those components, okay? So we've got a few options there to think about, okay? I'll get this question going. Let's see what everybody thinks for the current in our components if they're connected in series. So if you're not sure about this one, it might help to draw yourself a little diagram, maybe draw, a wire, put some light bulbs in it, think about the current going through the wire, think about what the current has to be at each point, at each component in the wire. All right, let's see what everybody thinks for this one. What's going to be the current in each of our components here? Let's take a look at what everybody thinks. Okay, nobody's thinking about option C, not going to be increasing. Maybe it's going to depend on the components. Maybe it's going to kind of decrease. Maybe it's going to be the same, okay? Now, this one can be a bit tricky because very often, if we think about having a, maybe a row of light bulbs, so it could be like, a row of like Christmas tree lights, something like that. And I think intuitively we think that, as the electricity is running along the wire, running along the components, we kind of intuitively think that it's kind of, sort of running out of juice as it's going along, okay? It's a bit like us as you get towards the end of a long day, you're kind of running out of energy a bit until you get to the end of the day. So I think it kind of makes sense why we might think intuitively that the current is going to progressively decrease at each point, okay? But remember that current, it's just how many electrons are flowing across a wire, okay? So maybe we're putting half an amp of current into our wire, okay? The current can't sort of build up, okay? We can't get like a kind of traffic jam sort of effect. If we've got, you know, one electron going in, we've got to have one electron coming out, okay? So even though it's quite counterintuitive, what we actually get is that the current, it's going to be the same for every component there. So option B, okay? So it might seem a bit counterintuitive. We're going to have a few more examples and we're really going to kind of understand this a bit more. And also we're going to figure out what actually is the thing that does progressively decrease with each component, okay? So very well done, everybody who gave that question a go there. Okay, now it might seem a bit surprising that it's option B, but next time we're going to be understanding the flow of current in circuits a bit more, and we're also going to be seeing, because there is something which does progressively decrease with the extra component, we're going to be seeing what that is, okay? Now, has anybody looked at their timetables for this semester yet? We're just talking about that. Has anybody? Okay, so they're a bit different from last semester, okay? So we've got our workshops on Tuesdays, okay? So we've got workshops Tuesdays afternoon, okay? So it's a kind of bit funny that we've got the workshops in the middle of the lectures and then our last lecture on Friday, okay? So just take a look at your timetable, see exactly which and when workshop you're in, okay? So we got our next lecture. Oh no, I think our next lecture is Thursday, okay? Or Friday. Anyway, I'll check my timetable too, okay? But the workshops are tomorrow afternoon. We're going to have a go with some of these questions, okay? So very well done today, everyone, with these questions. And I'll see you guys all tomorrow, okay? So I'll see you guys all then.